Hello, I'm going to give a quick demo of my Swift Student Challenge 2024. It's all about robots, which you should hopefully be able to see behind me. So yeah, let's get into it. Right, so let's get right into the activity. So you can see here, it's all about how robots move. So it's based off a industrial robot arm, the kind of thing that would assemble your car. And it's going to be talking about all the different movement styles and calculations to do with robots. So there's a few kind of teaching materials about different parameters. So you can see here it's talking about degrees of freedom, which is how many ways the robot can move. Joint limits, which is a bit like my arm. I can only move my arm to a certain point before it won't go any further. A robot has the same thing. A robot also has a workspace, so the reachable area by the arm. And it also has links and joints, a bit like how my arm has an elbow. And then what I did is I designed this robot in Fusion 360, which is some CAD software, and then I imported it into Reality Composer Pro and assembled it so I could get it so I could control the joints. And then I used RealityKit to measure the distances from the model, and then I can assemble what's called a Denevit-Hartenberg table. So you can see a diagram up here showing all the various distances. Quite complicated, but it's really useful for allowing us to build a table which we can use for movement calculations, which we're going to see a bit of now. So the first kind of movement style is forward kinematics, and that's calculating from the joint angles where the robot's going to end up. And helpfully, I can just plug in these numbers from these sliders here into RealityKit and get it to set the orientation of each component. But we can also do it mathematically, which is what is going on behind the scenes. So we're using the Accelerate framework, which allows you to do matrix multiplication. And we've got this matrix here, which uses the previous table. It will use those parameters within this matrix. I'm not going to pretend I understand what this matrix does. It's a pretty common robotics matrix for Denevit-Hartenberg homogeneous transforms, which you just multiply together and it gives you the endpoint. And then we plug that endpoint into RealityKit to draw this orange sphere. And you can see it calculates exactly where the ball's going to land without having to use any of the current kind of RealityKit maths that we already had. And then you can see here inverse kinematics, which is way more useful in actual practice. So it allows you to use the world coordinate system, it's called, and move along a certain line. So you can see here I can move along the x-axis, I can move along the y, forward and back. I can also move along the z-axis. I can also use the FRE rotation system, which is based off a common industrial robot rotation system that allows you to rotate around a point. And this is really useful for kind of if you imagine you're welding or something, kind of positioning your tool. And then from that, you can also see there's different solutions. So a bit like my arm, how I can get into certain configurations from different ways. You can also do that with a robot. And in this case, this robot, you can actually get into a certain configuration in 8 different ways. It's not the same for all robots. This robot is actually quite special because if you Google industrial robot arm, you'll see that a lot of them look like this because you can use a method that makes it a lot simpler to calculate where it's going to end up, and also it's quite reliable for positioning. But if you imagine a humanoid robot which can walk and talk and all those kinds of things, they're a bit more complicated, and these methods would not work for that. So to finish off, we've got a mini game, which is an AR. So I'm going to come over here, and then I'm going to press play, and then we're going to get our robot, which has appeared on the table, and then I'm just going to pop these balloons. So I have to orientate the robot and then pop the balloon with the arm. Oh dear, it wasn't close enough. There we go. And then over here, oh yeah, we've popped 2. And then, as you can see, the balloons are popping. There's an animation which I did in Blender, and the confetti on the floor is actually not intended, but I thought it was quite a nice feature, so I kept it in. But yeah, you can see I'm doing quite well here. And it's basically demonstrating how you might program a robot. In real life, they'd actually program a sequence, but for this, we're just manually controlling it, which you can do as well with the real robots, but they normally program it once and just get it to do the same thing over and over again, which is the good thing about robots. They can do repetitive tasks very easily. And there, you can see I got 8 pop balloons, which is a good score. And then this is the kind of ending screen, very nice. So I hope you enjoyed that. That's all for my submission. I really enjoyed making it. There was some quite complex maths, but it's good. I actually study this next year. I haven't done it yet, but this should be useful practice. So yeah, see you later. Bye.